Alright, so we're going to talk about a very important theorem in number theory called Chebyshev's theorem, and we'll probably need at least 2 videos for this, so I'll call this part 1. And so I guess like one of the most important theorems in number theory is the prime number theorem, which basically states that the number of primes up to x, let's call that pi of x, it's asymptotically x over log x. And what this really means is the limit as x approaches infinity of pi x over log x equals 1. So it's a very important statement. It was proved in the 1800s, I think, by Hadamard and de la Vallée-Poussin, if I'm saying his name right. And Riemann was on it too. His zeta function was important. So yeah, this is like a pretty cool theorem. And so I guess Chebyshev's theorem is sort of a weaker statement, but it's not weak, it's just weaker. And it basically states that there exists constants C1, C2 greater than 0, such that there exists such that C1 x over log x is less than or equal to pi of x, which is less than or equal to C2 of x over log x. So I think when Chebyshev was actually proving this theorem, I think its constants C1 and C2 were really good. They're like, this was maybe like around like 0.9, I want to say, and this one was around like 1.1. And so basically, you know, these are both like 1, so it was pretty close to the prime number theorem. So for this video, I will say we want to prove pi of x. We're going to prove the upper bound, C2x over log x. And so to start off with, we're going to show, we're going to think about the number n to the pi of 2n minus pi of n. So this is like n times n times n, and it's like the number of primes up to 2n minus the number of primes up to n is like the number of primes between 2n and n. It's like that many n's. And so really you can replace this. So your first prime that's bigger than n, like the very first one, this is already like less than that prime, call it p, and it's the same number of times. It's like the number of primes less than between n and 2n many times. And that, I mean, this is just like that first prime, but really this is less than or equal to the product of the primes between 2n and n. And you're going to have number of primes between n and 2n, many like primes between n and 2n, right? So that gives you that bound. And so I guess next we want to like keep going with our bounds. And so we see if we like think about the number 2n choose n, right? We know 2n choose n is an integer because it's like something choose something. and we can write this as 2n factorial over n factorial n factorial. Now, if we write this out, this is like 2n times 2n minus 1 times like n plus 1 over n times n minus 1 times n minus 2, etc. Now, we know, like, these are all the numbers between n and 2n. So we know all the primes between n and 2n are somewhere in this product. But all those primes are at least n, so they definitely don't divide the denominator. They're definitely not in there. And so we can safely say that this product of primes is less than or equal to 2n choose n. And so the next thing we could do is we can bound this, right? And I don't think this is a very good bound, but we have an exponential on this side. There's a log in our answer, so I'm guessing we want an exponential on the other side of this inequality. So, well, this is a binomial coefficient, so that reminds us of the binomial theorem. So this is definitely less than the sum from k equals 0 to 2n of 2n choose k, right? Because this is contained somewhere in the middle of this sum, and it's actually like the biggest number in that sum. But by the binomial theorem, we know that this is like 1 plus 1 to the 2n. You can imagine, like, snuck in here, there's like a 1 to the k times 1 to the 2n minus k, but that's just 1. So this is 2 to the 2n. And so now if we put that all together, we have n to the pi of 2n minus pi of n is less than or equal to 2 to the 2n. So when we take log of both sides, we have pi of 2n minus pi of n times log of n is less than or equal to 2 log 2 times n. Okay? So that's where now we have the logs we wanted. And so now we can try to come up. Now I guess the next thing we want to do is try to come up with a bound for pi of 2 to the n. And so I'm not going to be completely rigorous here, but we're gonna introduce a new function. So pi of x counts the number of primes less than or equal to x. And so perhaps I'll show this in another video, but we can use the first Chebyshev function theta of x, which is like the sum of the log of the primes. And it can be shown that the limit as x approaches infinity of theta x over x equals the limit as x approaches infinity of pi of x over log x. So showing pi of x is asymptotically x over log x is equivalent to showing theta x is asymptotically x. So you can sort of I won't say hand wavy, but you can sort of cross out these limits, cancel out the x, and you get the relationship that, I mean, if we're thinking about really big numbers, we could say theta of log x equals theta of x log x is about pi of x. Great. So then we could use that here, and really log of 2n grows on the same order as log n. When we're dealing with really big numbers, we can say statements like that. So this is really theta of 2n minus theta of n is less than or equal to 2 log 2 of n. So now what can we do? Well, if you look at this, we want to find pi of 2 to the n, so we're going to find like theta of 2 to the n and then sort of like flip it back. And so if you look at this, you can think, okay, what happens if I put in, theta of 1, right? Theta of 1, 2 times 1, I get 2 minus theta of 1 is less than or equal to 2 log 2 times 1. Well, if I plug in n equals 2, theta of 4 minus theta of 2 is less than or equal to 2 log 2 times 2. What if I do n equals 4? Because I want powers of 2. And I notice that 2 times the power of 2 is a power of 2. Oh, sorry, I'm off the page. Less than or equal to 2 log 2 of 4. And I could keep going all the way to theta of, let's see, what do I want to do? 2 times 2 to the n minus 1, which is 2 to the n, minus theta of 2 to the n minus 1, which is less than or equal to 2 log 2 times 2 to the n minus 1. And now I notice if I sum these all up, I get some nice cancellation, right? I get, like theta of 2 will cancel this theta 2, theta 4 will cancel this theta 4, theta 8 will cancel this. It's sort of like a diagonal cancellation. It's sort of telescopes. So then you have, if you add them all up, this doesn't cancel and this doesn't cancel. But if you look back at our formula for theta of x, theta of 1 should just be 0, right? Because there's 0 primes less than or equal to 1 to even begin with. And so if you sum those up, you get theta of 2 to the n minus theta of 1 equals theta of 2 to the n, which is less than or equal to 2 log 2 times the sum. So basically we have like a sum of powers of 2. So that's the sum from k equals 1 to n minus 1 of 2 to the k. Okay? But, alright, so what can we do now? Well, this is a geometric series. This is like 1 plus, like we call this sum s. And this is like 1 plus 2 plus 2 squared plus 2 to the n minus 1. And then so 2s equals 2 plus 2 squared plus blah, 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 plus 2 to the n. So then if we subtract these, we get nice cancellation. And we get 2s minus s equals 2 to the n minus 1. So s times 2 minus 1 equals 2 to the n minus 1. But 2 minus 1 is just 1, so s equals 2 to the n minus 1. And so then we get that theta of 2 to the n is less than or equal to 2 log 2 times 2 to the n, right? If the sum's 2 to the n minus 1, it's certainly less. 2 to the n minus 1 is certainly less than 2 to the n. So the next thing we can do is, alright, we have this sort of like this weird relation that we got from the asymptotics, that theta x log x equals pi of x. So that gives us that theta of x equals pi of x over log x. And so if you combine that here, we have that, let's see, pi of 2 to the n over log of 2 to the n is less than or equal to 2 log 2 of 2 to the n. So let's see, this on the bottom is equal to n log 2. Right. Let's see. Oh, I think I wrote this wrong. Let's go back. See, this is x over log x. So really, the log x is on the top. So we have theta x divided by log x equals pi of x. So theta of x equals pi. Theta of x equals pi of x times log x. Right. Okay, so this is saying pi of 2 to the n times log 2 times n is less than or equal to 2 log 2 of 2 to the n. And some log 2's cancel out, and we get pi of 2 to the n is less than or equal to 2 to the n plus 1 over n. Cool. So we're almost done. Now, if I hand you any x greater than or equal to 1, I can find n so that I have 2 to the n minus 1 is less than x is less than 2 to the n. Okay, so how can we use that? Well, pi of x is a non-decreasing function, right? So like, as I get bigger, as x gets bigger, like pi of x, right? The number of primes less than or equal to x as x gets bigger can only like increase. Like it can stay the same, right? Because like, you know, pi of 3 is 2. And if I go up to pi of 4, it's still 2 because, you know, 4 is not prime. But it's definitely not going to go down. So pi of x is less than equal to pi of 2 to the n because x is less than 2 to the n. Which is less than, and I'm going to write this suggestively, 2 squared times 2 to the n minus 1 over n. But we know x is bigger than or equal to 2 to the n minus 1. So this is less than or equal to 2 squared times x over n. Now what do we do about the n? Well, if we use this half of the inequality, we have that log x is less than n log 2. And that tells us that n is greater than log x over log 2. So if n is bigger than that, then so basically this is smaller than n. So if I replace the denominator of a fraction with something smaller, the whole thing's going to get bigger. So this is 4x over log x times log 2. So then in total we get pi of x is less than or equal to 4 log 2 x over log x. And that's exactly what we wanted, right? We wanted to find a constant c2 so that x over log pi of x is less than c2x over log x. So that's our constant, and that's our first half of Chebyshev's theorem. And let's see, log 2 is about 0.6 something, so this is bigger than 2. This constant is greater than or equal to 2. Well, it's definitely greater. It's 0.6 something. And so that's like compared to 1.1, like that's not that good, but it's a nice bound. So we'll do the other half of this inequality next time.